Today we're going to talk about the inverse of a relation, and inverse is really reversing a process. What reverses a given process? So if I say to you the inverse of squaring a number, most of you would probably say it's square rooting a number, but let's just dig in a little bit deeper as to why we say that. When we square a number, so if we take x and square it, if we take a number like 3 and we square it to get 9, when I say inverse, I mean what reverses the process. So if I say y equals the square root of x, it means that if I put 9 in, what comes out of that will be 3. The process has been reversed. The input and output of my two relations are reversed. Okay, let's do some other common inverses. The inverse of adding 3 to a number is, most of you would probably say, subtracting 3. So if I had y equals x plus 3, so if my input was 5 and I added 3, out would come 8. And so on my inverse relation, subtracting 3, if I put 8 into this relation, 8 minus 3, output for y is 5. Again, I've reversed the input and the output, the x and the y, the domain and the range. That's what we're leading to in terms of a definition. The idea of, or the inverse of multiplying a number by 2, what brings back what I started with? Most of you would probably say dividing by 2. Okay, so let's just look at this with equations. If I take 5, multiply it by 2 to get 10, what undoes that? Taking the number, dividing by 2, 10 divided by 2 gives me 5. And so hopefully with these examples you get the idea that an inverse is an operation that undoes the effect of another operation, and what you see happening above is that the inputs and the outputs are reversed. So what was x and y on the original relation becomes yx on the inverse relation. So let's look at this concept in a little bit more depth. I have a relation here in which I'm taking a value of x, I'm doubling it, and then I'm adding 3 to it. So the question is, what is the inverse of that? I multiplied by 2 and I added 3. To go in reverse, I would have to subtract 3 and then I would have to divide by 2. So my inverse should be, if I call my new starting point x, I would have to subtract 3 and then divide by 2. Now what I did here is I reasoned out that the equation of the inverse must be this, just by thinking about what the inverse operations actually were. You can also get this simply by reversing your x and y in your original equation, because we know that's what's going to happen with our points. So when you had y equals 2x plus 3, if you took x equals 2y plus 3 and you solve for y, subtract 3 and divide by 2, you're going to get what we have right here. So you can get the inverse in algebraic form by simply reversing the x and the y. Alright, let's graph these two relations together and see if we can notice anything else happening. So for this function, which is linear, we know, if we take some points and graph them, my graph is going to look something like that. If I graph my inverse, which is here, I'll put my table beside it. Of course, my point should be reversed, so -1, -2. Now let's just make sure of that. So if I plug -1 into my inverse, -1 minus 3 is -4, divided by 2 is -2. Yes, that's working. So the points are reversed. Now when I graph these reverse points, notice what's going to happen. Instead of graphing -2, 1, I'm going to graph 1, -2. So this point ended up here. Instead of -1, 1, here I'm plotting 1, -1. Instead of 0, 3, here I'm plotting 3, 0. here. Instead of 1, 5, I'm plotting 5, 1. And my graph looks like that. Now it's a little hard to show on a symposium as to how the points are moving, but essentially when I reverse the x and the y, the points are moving right across from each other, like so. They're moving across the line in the middle, which is the line y equals x. The points are being reflected across the line y equals x. And that's always true of an inverse. The graph of an inverse is always a reflection of the original graph about the line y equals x. By the way, just one more point to note. You'll notice that in this case, my graph, my inverse graph, is a function. And since that's the case, I often use this notation, f negative 1 of x. It's like f of x, but the negative 1 says it's the inverse of f of x is this. Okay? This notation is a little confusing. Don't think of f of negative 1 of x as it's not this. Okay? The negative doesn't mean reciprocal. Okay? Reciprocal and inverse are different concepts, which I'm sure will be reinforced in class. All right, so let's take a more complex situation, and this time I'm going to take my x, subtract 1, square the result, multiply that by 2, subtract 3 to get my output. And I'm going to begin just by graphing that relation. So that would have a vertex of 1, negative 3, and a vertical stretch factor of 2. So when on a regular parabola, y equals x squared, when I go over 1, I go up 1. The 2 says I'm going to go up twice as much, so I know that those are 2 points of accuracy. When I go over 2 on a regular parabola, 2 squared is 4, but the y is being doubled, so it goes up twice that far to here. And so my graph looks like so. And so now I'm going to draw the inverse, which I know is a reflection of the original graph about y equals x. And just before I do that, let's just state the domain and the range of the original graph. The domain of my original parabola is all reals, and my range is y is greater than or equal to negative 3. Which should mean that when I do my inverse, which I'm starting into now, my domain and range should be switched. So x should be greater than or equal to negative 3, and the range should be y is all reals. So inverting my point, talking them out, my vertex 1, negative 3 becomes negative 3, 1. 0, negative 1 becomes negative 1, 0. 2, negative 1 becomes negative 1, 2. Up here, 3, 5 becomes 5, 3. And the other points down here. And so my graph looks like so. If I want the equation of that, which is part of what I'm asked for as well, I'm going to take my original equation and switch x and y, because that's what happens when I do the inverse. And if I isolate for y, I can add 3. And I'm going to divide by 2 at the same time. Then I need to square root, which is plus or minus. Now the plus and minus, remember, means that 2 values are going to come out for a given x. And so I'm going to get y minus 1 on the right, plus 1. And the fact that I'm getting 2 outputs for an input of x means that my inverse is not a function, which I can see in the graph above. I can see that for a given x, for example here, there are 2 y's. And the reason for that is that on the original graph, the y had 2 x's. Now, it's alright that your inverse is not a function. The big thing is that you can't use the symbol. If your inverse is not a function, you can't use this symbol, because that says that your inverse is a function. So we just simply say y equals. So a couple of things I want you to notice here. First of all, that the inverse of a function is not necessarily a function. Examples right here. But often when we're working, we want to have an inverse, which is a function. Okay? So what we do is we restrict the domain of the original function so that its inverse is a function. And so as I just tried to describe above, that means that, remember, what's causing my inverse to not be a function is that each x has two y's right here. Reversing that to the original, that means that a given y is only going to be able to have one x. So not only is my original graph going to have to pass the vertical line test, it's going to have to pass the horizontal line test. Each x is going to have one y, and each y is going to have one x, something we call one-to-one, if we want an inverse, which is a function. So what we're going to do now is we're going to restrict the domain of our original function, f of x, which is in blue, so that our inverse, which is in red, is a function. Okay, I've just recopied the information from above, the main information from above, so we can see things a little bit more clearly. And as we said, the reason why the blue graph is not producing an inverse, which is a function, is because it's failing the horizontal line test. So what we basically have to do in this case is take away from the vertex either half of the graph. So what I'm going to do is I'm going to simply erase the left side of the graph. And so I'm changing my domain from all real numbers to x is greater than or equal to 1. And that's obviously going to change the range on the inverse to be y is greater than or equal to 1. And when I do the reflection across y equals x, it's going to mean that the bottom half of the graph disappears. Now you can take away either side. It doesn't have to be the right or the left. It can be either one. But you'll now see that we have an inverse that's a function. Alright, so this changes a couple of things in our equation. First of all, it's no longer plus and minus here because a given value of x produces one value y. And since we're taking the higher values, it's the positive one, the positive output of the square root. We can take away this. We don't want that anymore. So let's just erase it. And the other thing is, now that our inverse is a function, instead of saying y, we can say f negative 1 of x. And so by restricting the domain of the original function, we've created an inverse that is also a function.